Hello everyone. This is part two of the previous video where we were going through sample problems on geometric series. Okay, so we have some word problems in this section, so let's get started. Um, these first two problems are really just geometric sequence problems, just to get us in the right mindset for some of the other problems and just to get general practice. So if you find the first two simple and you already know how to do them, because we did similar problems to this in the previous set of sample problems I did on geometric sequences, feel free to skip forward to the part where I'm going over these problems. Okay, so let's get started with this. It says a car's value depreciates by 30% each year. If its initial value is 50,000, find the value of the car after 5 years. Okay, so we start with 50,000. And if the car depreciates by 30%, which is equivalent to a decimal value of 0.3, it's retaining 70% of its value. So it's keeping 70% of its value. Okay, so in other words, if the car is initially worth $50,000, the next year it's going to be worth 70% of that, or 50,000 times 0.7. The year after that, it's going to be worth whatever it was the previous year, so it's worth whatever it was the previous year, times 70%, so 70% of that. Okay, and it'll keep going like this. All right, so the common ratio here we can see is 0.7, right? We're multiplying by 0.7 every time. This is term 1, this is term 2, this is term 3. And here's something kind of important. The car's value depreciates by 30% each year, okay? So although this is our second term, this represents the car's value after 1 year, right? After 1 year, it's worth 70% as much. Okay, but this is the second term. So if I'm trying to figure out what the car's value is going to be after 5 years, I need to figure out what the sixth term is, not the fifth term. Okay, because term 2 represents what happens to the car after 1 year. Term 3 represents what happens to the car's value after 2 years. So the term number is always one more than the specific year we're talking about. Okay, so we're going to find a 6 here. And that's going to be equal to the initial value of 50,000 times the common ratio, which is 0.7, to the power of n minus 1, so 6 minus 1. So we get that a 6 is equal to 50,000 times 0.7 to the 5. And let's figure out what this is. 0.7 to the power of 5 times 50,000. Okay, so this will come out to 8,403.5. So after 5 years, the car is worth this much if it depreciates by 30% each year. All right, let's have a look at the next one. An investment of 2,000 earns 5% interest annually, compounded yearly. So we haven't really talked about what this means, compounded yearly. So if you're getting 5% interest compounded yearly, that means you're getting 5% interest each year. Okay, if we were instead getting 5% interest annually, compounded maybe instead of yearly, twice per year or every 6 months, that would mean that we get 2.5% interest after 6 months, and we get another 2.5% of interest after another 6 months. Okay, just as one more example, if we were getting 5% interest annually, compounded monthly, so 12 times per year, then we would take our 5% divided by 12, and what does this come out to? This comes out to around 0.147. So that means after the first month, we get 0.147%. After the second month, we get another 0.147%. After the third month, we get another one of this. Okay, so that's what compounded monthly would mean. We'll do a video on compounding interest and values like that at some point as well, but that's what that means. Now, yeah, so in this case it's compounded yearly, which means we don't get the interest in intervals. We just get one chunk. We just get everything in one chunk, 5% at the end of the year. All right, so let's do this problem now that we have the background. So it's initially worth 2,000 and earns 5% interest. So that means in 1 year, the 2,000 is going to be worth 1.05%. We talked about why there's a 1 here, and it's not just the decimal value of this, which is 0.05. And there shouldn't be a percent here. So yeah, I talked about the reason behind the 1 being there in the previous video, and the video about geometric series. Okay, sorry, geometric sequences. So if you want, you can have a look at the video I did on geometric sequences to see why the 1 is there. Here's a brief reason. The reason we have the 1 there is because after 1 year, we have the original 2,000 and 5% interest, 5% on top of that. So this 1 represents the original amount, and this 0.05 represents the amount we have on top of that. Okay, the year after that, we're going to have what we had the previous year times another 0.05. So times another 5% profit. Okay, so the reason it's 1.05 once again is because this is 5% profit. We have the original quantity of money as well as 5%. Okay, so we can see the common ratio is 1.05. And like before, this is term 1, this is term 2, this is term 3. Term 2 represents what our investment is worth after 1 year. Term 3 represents what our investment is worth after 2 years. So if we want, we're going to notice that the term number is 1 ahead. If we want to know what happens after 10 years, we have to figure out the 11th term. Okay, so let's go ahead and figure out the 11th term. So A11 is equal to the first term times the common ratio of 1.05 to the power of 11 minus 1. So A11 is equal to 2,000 times 1.05 to the power of 10. Okay, so let's see what this comes out to. 1.05 to the power of 10 times 2,000, and this comes out to, let's see, so we have that A11 is 3,257.789, so I'll round to $79. Okay, so this is how much your investment would be worth after 10 years. Okay, let's have a look at the next problem. Okay, so now these two are problems that really use the geometric series ideas instead of the geometric sequences, which we did above. Okay, so it says a ball is dropped from a height of 100 meters and bounces to 80% of its previous height each time. Find the total distance the ball travels after 6 bounces. Okay, so we're going to draw an image for this. So this maybe is a building or a structure that's 100 meters tall. Okay, and so the ball is dropped 100 meters, bounces. So here's the ground. Pictures really help for problems like this. So bounces up to 80% its height and then falls back down. Bounces up to 80% its height, falls back down. Bounces up to 80% its height, falls back down. 80% of height, falls back down, and so on. And we want to know the total distance traveled. So it goes 100 meters down, some amount up, some amount down, some amount up, some amount down, right? We want to add all of those up to find the total distance. After 6 bounces, so we have 1 bounce here, 2, 3, 4, 5, and we'll have 1 more as well. All right. Now I'm going to kind of highlight this first bounce with this pink color, just because it's a special bounce. It's the initial bounce, right? So first the ball just goes down by 100 meters, and then for the rest of the bounces, we can see they occur in these sort of more predictable manner, right? We see these sort of bumps after every round, right? You'll see a little bit more clearly why I'm doing this in a second. Okay, so let's write down some numbers. So first we drop 100 meters, okay, and then we bounce back up to 80%, which is 0.8 in decimal, 0.8 of the previous height. So that's 100 times 0.8. Okay, now, so that represents this distance going up, bouncing back up to 80% of the original height. And then the ball's going to fall back down the exact same distance, right? If the ball goes down to a certain height, it's going to fall down the exact same height. So let's erase this green thing. There we go. So because it falls down the exact same height, I'm just going to multiply this number by 2, right? It goes up and comes down, so multiply by 2. And this is another reason why I separated out the 100. We're going to see that all of the terms that come after this have a multiple of 2, whereas the 100 doesn't. So it's just simpler to keep them separate. Okay. For the next term, we're going to bounce up to 80% of the previous height. Remember, this was the previous height. So we'll go 100 times 0.8, and we'll bounce up to 80% of that, and then we'll fall back down, right? Which means we'll have 2 of that again. Okay, and we'll keep going like this. All right. So this represents the distance traveled after the second bounce, right? So this is bounce 2, this is bounce 3, and so on. Now, in our geometric, this is a geometric series, right? We can see that the common difference or common ratio is 0.8, right? We don't count the 2 because the 2 is common. It's the same. It doesn't change from term to term. What changes is this factor of 0.8. So the common ratio is 0.8. And like I said, I'm going to add in the 100 at the end. So I'll call this term 1, I'll call this term 2, and the next one will be term 3. Okay, now term 1, like we said, represents bounce 2. I'll write B2. Okay, so term 1 represents bounce 2. Okay, term 2 represents bounce 3. Okay, so because the first bounce was here, this guy's the second bounce, this guy's the third bounce, and so on. So if I want to know what happens after 3 bounces, I have to find the sum of this guy up to what? Up to one term before term 6, right? So we're going to notice that the term number is always 1 behind the bounce number. So the 6th bounce, so bounce 6, is going to correspond to term 5. Again, that's not including the 100. So we're going to go ahead and figure out what term 5 is, and the sum of the terms up to term 5 is, and add 100 to that. So let me erase this, and we'll do the math here. So the sum of the first 5 terms is equal to the first term, which is 2 times 100 times 0.8, right? That's the first term here, times 1 minus the common ratio, which is 0.8 to the power of 5, because we want the 5th term, all over 1 minus 0.8. So let's see what this comes out to. S5 is equal to, so 2 times 100 times 0.8, that's 160, and then we have 1 minus 0.8, oops, that should be to the power of 5, and then brackets, 0.8 to the power of 5, and this is 0.672, oops, forgot to subtract 1. No, I did subtract 1. This is 0.67232 all over 1 minus 0.8, so that's 0.2. So let's see what this comes out to if we multiply everything together, times 160 divided by 0.2. So this comes out to 537.856 meters. And remember, the S5 we just found here, that's the sum of all of these. We still have to add the initial fall of 100 meters. So I'm going to erase this now. Right, so again, remember, we're adding in the initial fall of 100 meters because the sum we found didn't include the initial 100 meters. So the total distance traveled is this number plus 10. So 537.856 plus, sorry, I think I said 10. I meant 100. 100, which is 637.856 meters. Okay, so that's the final answer there. All right, let's have a look at the next one. So it says the first term of a geometric series is 128 and the fourth term is 16. Find the sum of the first 6 terms. Okay. So the first term of a geometric series is 28. So that's our 128. That's our A. The fourth term is 16. Find the sum of the first 6 terms. So the sum of the first 6 terms will be equal to the first term, 128, times 1 minus the common ratio. Now we don't know the common ratio, to the power of 6, because it's the sum of the first 6 terms, all over 1 minus r. So the only thing we have to do here is to figure out the common ratio. Okay, let's do that here. How can we figure out the common ratio if we know the fourth term and the first term? Well, we've done examples on this, on how to do problems like this in the geometric sequence video. So if you guys have any issues with that, go and watch that. All right, essentially what we're going to do is the following. I'll give a brief explanation. We know this is the fourth term, so I'll use my nth term formula and say 16 is equal to 128 times the common ratio, which I don't know, to the power of, this is the fourth term, so 4 minus 1, right? So we're going to use this now to figure out what r is, right? The logic here is that if we wanted to figure out what the fourth term was and we knew the common ratio, we would set up the formula like this and go to the power of 4 minus 1. But now we know that this is 16 and we don't know r, so we're going to solve for r. All right, so this is going to be 16. I'll divide both sides by 128 first. So this comes out to 1 over 8 is equal to r to the 4 minus 1, or 3. And if we cube root both sides to get rid of the power of 3 for r, we get that cube root of 1 over 8 is 1/2, because 1/2 times itself, 3 1/2 times themselves will be equal to r. So our common ratio is equal to 1/2. Now we're going to plug that into this formula, the sum, to figure out the sum of the first 6 terms. So that's going to be 125 times 1 minus 0.5 to the 6, right? That's just 1/2 in decimal, 0.5, all over 1 minus 0.5. Okay, let's erase the stuff here and figure this out. So S6 is 125 times, let's see what this is, 1 minus 0.5 to the 6. So this is roughly 0.984375, all over 1 minus 0.5 is 0.5. So let's multiply all of this, and this comes out to let's see, 246.09. No, something isn't right here. We can't have the sum of the terms be a decimal. Okay, let's see what happened. I think I might have plugged this in incorrectly. Let me try this again. 1 minus 0.5 to the power of 6. Okay, so it's that number. This was 128. Sorry. First term was 128, not 125. Okay. So let's multiply that. Let's fix the issue. I'll do the multiplication again. Okay, this comes out to 252. Okay, so S6 is 252. Okay, so I will stop the video here just because it's getting a little bit long. We'll go over the remaining 3 problems under the advanced problem section in the next video, so there will be a part 3 to this. These 3 problems, the first 2, or the first one is similar to one of the ones we did above, and this one is fairly decent as well. It's a good problem. Number 3 takes a little bit of time to solve, which is why I've decided to have these 3 be in their own video. So that'll be it for this video. If you guys have any questions, please feel free to put it in the comment section, and I will see you in part 3.